Strap yourselves in, grab yourself a cup of coffee, and get ready to talk about quantum mechanics. And at least for this course, the level of depth will be that quantum mechanics tells us about the location of the electrons in the atom, and it tells us about these locations in terms of probabilities of finding the electron. And the math gets pretty intense here, and we're going to basically present the results with a tiny bit of background. Schrodinger's equation, which is this equation that I'm showing here, allows us to calculate the probability of finding an electron with a particular amount of energy at a particular location in the atom. And the solutions to the Schrodinger equation are called psi. And the psi symbol is here, and psi is called the electron probability wave function. And a couple things we will know about psi, and that's all. First off, psi is largest, closest to the nucleus, and that's because the electron is attracted to the nucleus. So psi largest, closest to nucleus. And that again, that's because the electron is attracted to the nucleus. And then psi oscillates or has the form of an exponentially decaying sine wave as you get farther from the nucleus. So psi decays, or so oscillates. Psi oscillates, that's the word I'm looking for. Like a wave. And I guess that's all we need to know. You can always come to office hours and ask me questions about more information about psi, but we really don't need to know it for this course. Okay. Now, B, the solutions to Schrodinger's equation, which are in terms of solutions for psi, the electron probability wave function, lead to or define orbitals, or give 4 quantum numbers that define orbitals that the electrons are in. We look at the first 3 quantum numbers this chapter, and we look at the last quantum number in the next chapter or lecture outline. And what I'll note here is that each orbital is defined as the volume of space in which there is a 90% probability of finding the electron. That is the definition of an orbital, and we will see that the shapes are pretty varied, but that is always the definition of the orbital. And if your question is, why not include 100% of the probability of finding the electron? Well, to get truly 100%, you would have to extend the orbitals all the way to infinity. Like I said, there's an exponentially decreasing chance of finding the electron, or an exponential part of the wave function that gets exponentially smaller all the way out to infinity. And having orbitals that are each the size of infinity is not useful. It's found that the 90% probability is a useful place to set it, and that's because the orbitals will approximate other properties that we find, such as the sizes of atoms. Now, the first quantum number is the principal quantum number. That is called n, and it describes the main energy level or shell that an electron occupies. And the principal energy levels are similar to the Bohr energy levels. And what I'm going to do is I'm going to zoom out a little bit here, make sure I can see my whole page. And I'm going to divide my page in half here approximately. And we're going to look at the Bohr energy levels in terms of two variables. So the first one, and I'm going to do this on the right here, is going to be size. And the size of n, which are the principal energy levels, increases as n squared. So if we were to draw an atom with the nucleus right here, and we were to draw n equals 1, and I'll draw n equals 1 fairly tiny, we would then have to draw n equals 2, 4 times as big, 1, 2, 3, 4, approximately there, and let's see how this goes. So, and I'll make a note, so 4 times as big. And then if I were to make n equals 3, it would have to be 9 times as big, approximately out here. And very quick soon we run out of space for these. And typically we don't draw them proportional to their size. We typically draw them approximately equal spaced, but this seemed like a good time to introduce this variation in their size. And so that's size of n. And then there's the energy. And the energy of n increases as 1 over n squared. So those are opposite functions there, that's true. But what that leads to is if we now think of energy, and and we've done this before, or no, we will do it soon. If we think of the energy and the nucleus down here, then the n equals 1, if we draw it right there, and then we do n equals 2, it's going to be 1/4 as bit far away as here. So let's divide that into 4, approximately there, and then it gets 1/9 as far, and then it keeps going until somewhere up here you get n equals infinity. And all of these values are valid values of n. So n equals 1 all the way through n equals infinity are valid values. So the Schrodinger equation and the principal quantum numbers that come out of the Schrodinger equation and the psi functions, the wave functions, says there's no limit all the way out to n equals infinity. What we will say, though, is that for n equals infinity, that is the definition of when the electron has left the atom. And that'll be an important part. So that's equivalent to saying that the electron is no longer part of the atom. And what we will do is we will also call this when the electron has left the atom, so the atom is ionized. And if you were to take a hydrogen atom with its electron in n equals infinity would be H+, because it's lost that electron, therefore the term ionized. Now, these rungs or these lines here are oftentimes called, especially in my class, like the steps on a ladder, although they're not equally spaced. And we will call this kind of diagram from low to high energy as a ladder diagram. Though it would be a pretty hard ladder to climb. But now, and so these values of n are the same values of n here and the same values that we've been talking about before with that E equals minus 2.18 times 10 to the minus 18 formula that we have used and will use again. Now, the angular momentum quantum number is L, and oftentimes when I write it, at least, I'll use the cursive letter L. The angular momentum quantum number describes the shape of the orbital. Each value of L has a specific shape. So there's two things we want to say about this. First off, L goes from 0 to n minus 1. And we'll show you what that means coming up. And then let's see. So if we draw a little table here, and we say L, and then we say, well, the L values will also be associated with letters. And those letters will have certain shapes for us, as we'll see. And so L equals 0 is what's going to be called an S. L equals 1 is going to be a P. L equals 2 is going to be a D. And L equals 3 is going to be an F. And each of these shapes will have specific values, each of these letters will have specific shapes. And so an L equals 0 will always be an S shape and what we'll call an S sublevel. So I will also write, so these are sublevels. Okay. And again, we're just sort of reviewing how these quantum numbers work, and then we'll see them in action. The magnetic quantum number m sub L designates the orientation of the orbital within the sublevel. And so we go from n to L to m sub L, and m sub L goes from minus L to plus L. Minus L to plus L. So as an example of that, well, let's save the examples. That's an L cursive. And typically, what m sub L is identified with is the number of m sub L values is equal to the number of orbitals in a sublevel. Okay. And okay, so those are the three quantum numbers we're going to deal with in this lecture outline. Let's do the first principal energy level. That's for n equals 1. And for n equals 1, L goes from 0 to n minus 1, so 1 minus 1. L goes from 0 to 0, which just means that L is 0. And so that is an S sublevel. And so M sub L goes from minus 0 to plus 0, which for us just means, it's not a math class, those are not different numbers. It just means that M sub L equals 0. One value equals one orbital. And so what we get in the first principal energy level is 1s, and that is the sublevel, and that is also one orbital. And as far as shape goes, so the s sublevels and the s orbitals are going to be spheres. And there's a picture of the 1s orbital that is part of the 1s sublevel. So 1s orbital that is also the 1s sublevel. Now, if we're at that If that was it, then life wouldn't be so bad. Now let's go on to the second principal energy level. Like I said, now for n equals 2, L equals from 0 to 1, which means there will be L equals 0 and L equals 1. We'll handle both of those differently. Remember we said for L equals 0 that that was an S sublevel with 1 orbital. And we're going to call this the 2s. So the n is the 2, L equals 0 is the s, and the fact that there's one value means that the 2s sublevel has 1 orbital. And now we'll go ahead and just say that similar to what we've said before for n equals 1 and n equals 2, so the 2s will be larger. And again, we said that the 2s, well, let's draw 1s. Let's draw the 2s. It should be 4 times larger. We'll draw it as large as our axes permit, although it's supposed to be symmetrical there. We'll call that 2s. And the s sublevels, which have 1 orbital each, are very similar to just the Bohr model of the atom before. But now let's talk about L equals 1. For L equals 1, we said that was, well, we're still in n equals 2. Now we're in L equals 1 is for a p sublevel, and the 2p sublevel has 1, 2, 3 orbitals. Okay. And those 3 orbitals are generally designated as 2px, 2py, and 2pz, with x being a subscript here and the other 2 not being subscripts. 2px, 2py, 2pz. And to show you what those look like, we'll draw a set of axes. And remember, L determines the shape, so all of these will have the same shape, and these numbers determine the orientation of those shapes. So I'm going to define my axes as x and y, and 2px is going to be dumbbell shapes or balloon shapes, 2 of them along the x-axis. And this is going to be 2px. It is 1 orbital with 2 parts. Okay, and so that means that this is the shape, since that's 1 orbital, that is the shape in which you can find what we will call the 2px electrons 90% of the time. And as far as the y-axis, or 2py, so it's the same shape oriented along the y-axis. I'll attempt to do that. And they're supposed to be the same size. And you'll notice that, get in there. So none of these parts touch the nucleus. None of them touch the origin. And so that is a good thing to draw if and when you're asked to draw these. So I'm just going to write up here, doesn't touch nucleus. Okay. And then the other thing I'll tell you is that this surface, this plane that is the YZ axis, is what we will call a node. And a node is a surface with no probability of finding the electron. A surface with no probability of finding the electron. And one of the strange results of quantum mechanics is that you can find the 2px electron over here. You can find the 2px electron over here, but you cannot find it on this plane between the two parts. Anyway, we've seen that quantum mechanics is an interesting subject. That is one of the results. Again, here, there's a plane right here in the xz plane in which there is also a node. We can draw that too. So you can see the shape of a p orbital for which L equals 1. And you can see there are 3 orientations, well, 2 of them so far. The third one, 2px, is the same shape along the, 2pz is the same shape along the z-axis. And of course, the way I've drawn it, the z-axis is coming out of the page, so there'd be a third one coming out of the page and going down into the desk here. Okay, and just because it's a little complicated, we won't draw it, but you get the idea. Okay, for n equals 3, that's the third principal energy level. So L goes from 0 to 2. We have L equals 0, which is 3s. 3s sublevel has 1 orbital. (3p) for L equals 1 has sublevel has 3 orbitals. And now for L equals 2, this is going to be 3d, and there are 5 orbitals. So 3d sublevel has 5 orbitals. And what you'll notice about those orbitals, well, an s orbital had 1 part and it was a sphere. A p orbital had 2 parts. And now these are more complex. So some of them have 4 parts, some of them have 2 parts and a donut. And so all of these have similar levels of complexity, even though we have a different shape down here. And they're all getting more complex. And how we can think of that is that for the n equals 3 level, we've stuffed some electrons in it already, and we're trying to sort of squeeze some electrons in between all the other orbitals. And you don't have to know how to draw these. You do have to know how to recognize them. And really tell them apart from the s orbitals, the p orbitals, and the f orbitals, which are coming up. And then I guess the one other thing I'll say is that each d orbital has 2 nodes. And the shapes are just getting more complex. Well, this will be our last page for this video. The fourth principal energy level has n equals 4, L equals 0 to 3. We have 4s, 4p, 4d, and now 4f. And the 4f sublevel has 7 orbitals. And we will see that the 4f's are all more complicated than the d's, some of them having 8 pieces, some of them having 2 donuts and other shapes. And you should be able to recognize these as well and tell them apart from the other orbitals in case you are given shapes on an exam in which you are asked to identify which one is the f orbital or one of the other ones.